Physics has hundreds, if not thousands, of physical quantities, and they differ a lot, not only in what they represent, but also in their mathematical nature. So much so that physics is like a big zoo with all these different animals. Some walk, some crawl, some swim, and some even fly. By that I mean these quantities behave differently even in simple operations like addition. We will see two major categories of these quantities in this chapter, and we are going to start with some simple examples. Let us start with time. So here we have a recipe given which takes about 5 minutes of preparation time, 15 minutes of actual cooking, and then we need to set it up for about 10 minutes, and then it is ready in 5 plus 15 plus 10 equal to 30 minutes. So we can simply add these times to get the total time required. Length behaves the same way. For example, here is a piece of furniture. It has, say, these three compartments. One is 12 inches long, the second one 24 inches, and the third 12 inches long. And we can simply add these lengths to get the overall length of this piece of furniture. So 48 inches is a simple sum of these three lengths. Mass behaves the same way. So here we have a 12 pack of, say, popcorns or something, and each is, say, 25 grams. Then totally it will make 300 grams. And if they throw in one extra, well, you just add those 25 grams to get the total mass of 325 grams. Volume behaves the same way again. So here we have a small tanker, and it has three compartments as shown here. 1500 liters, 1000 liters, and 1500 liters again. We simply add them to get the total volume. And there are many quantities in physics which behave the same way. Say energy, work done, voltage, electric current, temperature, they are everywhere. These are the simplest of quantities you can find in physics. Now you must be thinking, what's the big deal? Isn't this how all quantities behave? Isn't 2 plus 2 always 4? Well, unfortunately, things are not always this simple. And therefore, we are going to group these simple quantities in a category of their own. We will label this group as scalars. So scalars only have a magnitude, which of course includes a sign if they have one, and appropriate units, and they can be added or subtracted like simple numbers. Next, we are going to look at quantities where 3 plus 4 could be 7 sometimes, or could be 1, or could be anything in between 5 or 6 or 3.8. Let's see that. So here we have a dolphin which is capable of swimming at 4 meters per second, which is kind of leisurely for dolphins, and it's in a river right now which is flowing at 3 meters per second, which is pretty brisk. We want to know what is the effective velocity of this dolphin. Now most people would immediately ask, well, it depends on the direction. So what is the direction in which the dolphin is swimming? So there are these different cases. The first case we would consider is the dolphin is swimming along the current. And in that case, on its own, the dolphin is going to move, say, 4 meters in a second. So this is how much it will swim in a second. And the current would carry it 3 meters further. So in 1 second, the dolphin is going to move 3 plus 4 equal to 7 meters. And therefore its speed or its velocity would be 7 meters per second. Now let us consider the next case where it is swimming against the current. In this case too, like before, the dolphin would swim 4 meters, of course in this direction this time, and the current, however, is going to push it back, and it's going to push it back by 3 meters in a second. And therefore the net displacement of the dolphin in that 1 second would be just 1 meter, and therefore its velocity would be 1 meter per second, because the whole thing is going to happen every second. So far nothing surprising. Even some of the scalars behave the same way. They may have positive and negative signs and cancel each other, like these velocities are doing to some extent over here. But the next case is really very interesting, where the dolphin starts swimming across the current, perpendicular to the current. In this case, the dolphin is going to move 4 meters in this direction, but the current would carry it 3 meters in that direction, and therefore the effective displacement of the dolphin would be from this point to that point in an inclined direction like this, and its magnitude would be 5 meters. And this is going to happen every second. So the net velocity of the dolphin is going to be 5 meters per second. Mind you, this is neither the sum nor the difference of 3 and 4. So something quite different is happening now. Something that never happens in the world of scalars or pure numbers. And therefore these quantities that we are dealing with now, like velocity, are quite different animals. And therefore we group them separately and call them as vectors. So when we are dealing with vectors, we should not only consider how large they are, what is the speed, 3 meters per second or 4 meters per second, but also its direction. Now let us see this vector addition in its most generalized form. So far we saw only 3 special cases where the dolphin was swimming across the current. So we got the effective velocity of 5. We saw when it is moving along the current, the effective velocity is going to be 7. And when it is moving opposite to the current, the effective velocity is going to be 1. But really speaking, the magnitude of velocity could be anywhere between 7 and 1. All possible values between 7 and 1 could be taken just by changing the direction of dolphin's velocity. So all these values are possible. We'll be looking at vectors in detail in subsequent videos, like how they are represented, how they interact with scalars or other vectors, what operations we can do, and so on. But before we close, a word of caution. Although vectors are quantities which have magnitude as well as direction, not every quantity that has a direction and magnitude is a vector. If you want an example of this, click this link.